Yeah, it's being recorded. And I will share my screen. Okay, so today is the day when we finally finish the math and get back to the signal. Okay, so let me do a very quick recap of what we have been doing. Um, so we looked at the sampling theorem, which essentially says that you can sample the signal at more than twice the maximum frequency content of the signal, and then the samples actually can contain exact all the information about the signal essentially, because you can reconstruct the signal back from its samples. So there are some convergence issues that are there, but we won't deal with those in this course. So we'll just uh, we'll just go ahead with this idea that I've talked about. So here's the sampled signal x of nt multiplied by a comb function. The comb function is shown here. In the frequency domain, it's again a comb function. So essentially, you end up making infinite copies of this. So this is the Fourier transform of the original signal, here shown on top. This is the Fourier transform. It's still the Fourier transform of the sampled signal. Okay, and if you're sampling fast enough so that omega s is more than twice of omega m, so then there is no aliasing. Here there is some aliasing in which the two lobes sort of um, you know uh, interfere with each other, or basically they cross each other. If that is not the case, you will be able to recover the signal from its samples just by multiplying in the frequency domain with a ideal low pass filter, which is a rect function like this. If you multiply this function with that, all these side lobes will go away and you will be left with this. Okay, and that's the way to reconstruct the signal from its samples. You multiply the signal, the Fourier transform of the signal with the Fourier transform of with a rect function, which is like this. And in the equivalently in the time domain, it's a convolution of the sampled signal with the Fourier transform of a rect function, which is a sinc function. So as long as you're convolving with a sinc function, you'll get the signal back. Okay, and yeah, it sounds quite amazing that all you've got are some samples and you are able to reconstruct it perfectly. But that's how it is. It's quite amazing. And then we talked about the fact that this signal, the sampled signal, is still in the time domain. So it is still on a time axis with t, 2t, 3t having these delta functions and 0 everywhere else. I can equivalently discretize it so that it becomes a function of n now. So it's xdn. There's no time information. It's just 0, 1, 2, 3, 4 up to n. And turns out, if I look at the DTFT of this signal, this is a discrete signal. So I will take its discrete time Fourier transform, which is again a continuous function in the frequency domain. Then the Fourier transform of the original sampled signal and the discrete time Fourier transform of the samples given by this, they are intricately related, as you might imagine. And how they are related is that if you look at the Fourier transform of the sampled signal, you get this. These are infinite copies, with this being the omega axis, and this frequency here is omega s. It's 2 pi by t1, which is the t1 is the sampling rate. And when I look at the DTFT, I have just lost information about the omega s t1 here, because I have lost information about t. It's only sample in s. So I end up getting a period of 2 pi. note that it doesn't contain any information about the sampling rate itself. Okay, so and that's the only difference. Otherwise, they look very much the same, which means that the DTFT is nothing but the Fourier transform at omega by t. So notice that there's information about t here, which is sort of lost there. Okay, and if you change the sampling rate, these lobes will come close or go far. For example, here I have reduced the sampling rate by increasing the sampling interval. So the lobes have come closer to each other. And in the DTFT, again, it's a conversion of 2 pi by T2 to 2 pi. So I've again lost information about this. This has a period of 2 pi. This has a period of 2 pi by T2. Okay. So that's that. That's the relationship between the sampled signal and the DTFT. And finally, we talked about the discrete Fourier transform in the last class. And this discrete Fourier transform is nothing but the discrete Fourier series of a periodic signal, which is constructed by taking infinite copies of the original signal that is given to you. So you always take DFT of a finite length signal. Practically, that's always the case, right? You can't deal with infinitely long signals. If you have something in MATLAB, for example, some array, it will have some length, like 4096 samples, which I had given you earlier. So you take those 4096 samples and you make an infinite number of copies of them translated to get a periodic signal. Now, the advantage of having a periodic signal is that the discrete Fourier series coefficients only have n terms. It's the same number of terms as the number of samples in the original signal. Remember this. Let me just go back here. This is what I'm talking about. This is Fourier. If you have got a signal that is periodic in time with a period of n, its frequency domain representation also has n terms going from 0 to n minus 1 given by this, and it's a cyclic convolution. So this summation here is over n intervals, n samples. This we had done a long time back. Turns out, this is the important part, that if you look at these discrete Fourier series coefficients, it will be the same as the DTFT of the finite length signal without the periodicity. So if you now look at a finite length signal which is zero everywhere else and construct its DTFT, the DFT is nothing but the samples of the DTFT between 0 and n. So you take the DTFT, which is a continuous function in omega, and you look at n equal samples in the frequency domain, and that is what the DFS coefficients are going to be. Okay, so that's the proof that we did in the last class towards the very end, and I had said that we will repeat that today. So essentially what I have done is, so by the way, if this is confusing you, you have every right to be confused. This is actually very confusing the first time you see it. It's quite all right to be confused over this. It's a lot of stuff here which are all very sort of related to each other, and it's very hard to sort of make out the differences when you first see all of this together, and which is why it's introduced very slowly of exercise on that, so that everything settles in slowly. Here, over a period of only 7 or 8 classes, we have covered a lot of stuff. So it's okay if you are confused. You just have to read this over and over again. As I mentioned, the books are so nice that they carry all the information that you need. So here's the proof. This is now taken from Oppenheim, Schaefer, and Buck, which is the discrete time signal processing book. This is the second book in the series. here what I'm doing is I'm starting with the aperiodic signal xn, but it's an aperiodic signal with some finite length. It's zero everywhere else other than over an interval of n. So I can look at its DTFT, and this is how it's going to look like. Fourier transform is x e to the power j omega, where now omega varies between, well, omega is continuous, but it's periodic with a period of 2 pi. And I'm going to take n samples of this. So assume that a sequence xk is obtained by sampling x e to the power j omega at frequencies given by this. So the first sample is at omega of 0, the second sample is at 2 pi by n, third sample is at 4 pi by, the last sample is at 2 pi n minus 1 by n. The n plus 1th sample is again 2 pi n by n, which is 2 pi, which is the same as the 0th sample. Okay. So this is a periodic signal now with a period of n given by this. But because it's a periodic signal with a period of n, it could potentially be the discrete Fourier series of some sequence xn, some periodic sequence x tilde n. So I'm going to try to find out what that periodic signal is going to be. And I'm going to show you that the periodic signal is nothing but this original signal repeated infinitely, translated and repeated. If I do that, then I'm done. Because that means that if I take the original signal, make infinite copies of it, infinite copies, and stick them one after another to construct this, the DFS that I'm going to get shown here is nothing but the samples of the DTFT of the original signal at n equal intervals. Okay, so that's that. So now let me look at show you the proof. The proof is actually quite straightforward. I'm going to say that this is a discrete Fourier series coefficient. So I can actually construct my original signal by just using the the synthesis equation, which is given by this. This is the same as this formula here. Xn can be constructed by doing this. Here ak is your x tilde k, that's the coefficient here. And I'm just writing this e to the power jk 2 pi by n in a slightly fancy way, like this. So I'm writing wn as e to the power minus j 2 pi by n. And then we take a power of k here, and because there's a minus here, I put a minus there also. So this is nothing by e to the power j 2 pi k by n, which we have seen earlier here, e to the power j k 2 pi by n n. Okay, so I'm just using the synthesis formula, that's all. So this is xn, but now I use the fact that x tilde k are the samples as shown here of x e to the power j omega, and x e to the power j omega is given by this, because this is the formula for DTFT. Okay, so again, let's going back to this thing here. This is the DTFT formula for a periodic signal. Okay, so xn is now aperiodic in time. So this is the formula for that. And I'm just putting that in here. Okay, so x e to the power j omega is that. So x e to the power j omega at omega of 2 pi by n k is just going to be this. And I note that e to the power minus j 2 pi by n is just wn. Wn is e to the power minus j 2 pi by n. So this term here is just Wn minus Km. Sorry, minus is taken care of because it's e to the power minus j2 pi by n, which is Wn. So this is Wn Km and this is Wn minus Kn. So together it becomes Wn minus K of n minus m. Okay, so there's just a little sleight of hand here, nothing much. I'm just writing e to the power minus j2 pi by n as Wn, and I'm just putting all the Wn terms together, and there's a double summation here. So I take this summation here, xm, and this whole summation here is over k. Okay, is this fine? This is the only tricky step here. This is okay, right? If this is confusing, let me know. Um, can one or two guys just say yes or no? Either one is fine. Can you guys hear me? Hello?
I'm not very clear with the sampling of omega n. Means when you take omega n power minus k.
Yeah. Okay. So let me write this down. So is this fine? Is this okay? This is by definition. Definition of D as given here. I'm using just this formula. Okay, so xn is a finite length but aperiodic signal. It's a signal that is taking some values over n but is zero everywhere else. So this is 0, this is n minus 1, and then it is 0 everywhere else. So I can take its dtft, and it's given by this formula. Here. And now xk by definition is just the kth sample between 0 and n of this function. Sorry, between 0 and 2 pi. Okay, so this is x e to the power j omega is a function which is periodic with a period of 2 pi, as is every dtft. I'm just taking n equal samples between 0 and 2 pi. That's what this is. The kth sample is just omega 2 pi. I have divided in segments, right? So I have divided segment is just 2 pi multiplied by k. Is this fine?
Yes.
The value of this is x e to the power j omega, and I'm just putting the value of omega. One second. So my fancy pen has a button. If I inadvertently click on it, it just creates all these things. Okay, I'm back. So all I am doing here is putting the value of omega as 2 pi by n k as here. Because xk is just x to the e to the power j omega at omega equal to 2 pi by n k. So I'm just here. That's it. Omega is taking this value here. Okay, and then I notice that there's a summation over k, a double summation. So I can interchange the order of summation. So m comes out here, m here, this k comes in, and all doing now is this and this together. And note that omega n is just a w is just a shorthand of this. And here, so e to the power minus j 2 pi by n is just wn. So this term here is just wn, sorry, wn here to the power km. That's it. And you have the wn minus kn here outside. So together, it's just wn minus k n minus n. Okay. Going from k0 to n minus 1, and you also bring in the 1 by n here. So that's that. Is this fine?
Yes.
So now the question is, what is this function here? Actually, let me just say n minus m is some number r. So what is 1 by n summation of k 0 to n minus 1 wn minus kr? See, this whole thing, when I sum over k, is going to be some function of r. So can anyone, and suppose I'm plotting this function as a function of r. When r is equal to 0, what is this function? For r equal to 0, what is this function?
Summation k by n.
Wn, when r is 0, what is wn to the power 0?
1.
1.
And
Right? So each of these terms will be 1. So the summation will be n by n is 1. So at r equal to 0, this function takes a value 1. Okay, so this is fine, right? I mean, for r equal to 0, this function, each of these terms is 1. So it's a summation of n ones, which is n. So n by n is 1. So whatever this thing is, when r is equal to 0, here I'm just denoting r as n minus m. It's going to be 1. Now, when r is equal to some factor of n, some multiple of n, like r is equal to n, let's say, what is it going to be?
will one.
Why will it be 1?
Because it's means we have taken a sample, so it's a periodic right now. So again, the value will occur at the same point. Means
Yeah, so it's basically what you have here. This is omega n, which is e to the power minus j 2 pi by n, right? So omega n multiplied by any factor of any multiple of n, like n or 2n or 3n or kn, just be e to the power minus j 2 pi k, which is again 1. Okay, so at n or at 2n or at 3n, this thing becomes 1 again, this whole thing. And at every other point, it is actually 0. we have done this proof before. It's basically looking at k vector, sorry, n vectors. So e to the power j 2 pi by n can be thought of as a complex number, and I'm just looking at, so this is the first one, this is the second one, this is the third one and fourth one, and they always sum up to 0 unless the first one is here. Then they are all, even if you multiply, you get the same ones, and then it becomes n. This is the proof that we used early on to prove a bunch of things. I hope that this you guys remember. Okay, so this was Fourier transform. Sorry, here. So I have told you earlier that there are two things that we need to really, remember very well. In the continuous domain, this integral is important, and that is what is used to get the discrete Fourier coefficients by doing this multiplication, and its equivalent discrete version was this one. Okay, and I am just telling you this thing only. There's nothing else. E to the power j 2 pi by n is now wn. So this thing is just wn minus kn summation over some k n minus 1. And this is n, and it's periodic. So even if you take n as some k as some multiple of n, so it's going to be the same. So at 0, n, 2n, 3n, it's going to become n, and it's 0 otherwise. Okay, so basically doing this thing only. There's nothing else. And this we had done earlier when we were looking at discrete Fourier series and so on. So this is the same proof that is coming here. At the end of the day, that's all we have. These two things that we have to understand. So this thing becomes 1 at 0, n minus m, 2 times n minus m, and so on, and is 0 everywhere else. If I make this some number r, this is how it's going to look like. So it is nothing but an impulse train. It is nothing but an impulse train given by this. It's an impulse train which becomes equal to 1 whenever n minus m is some multiple of n. Either n minus m is 0, or n minus m is n, or n minus m is 2n, and so on. Otherwise, this is 0. Okay, so this is an impulse train that we have got. So our expression here is just xm multiplied by this impulse train, but the factor here is n minus m. And now if you look at this, this is just the convolution of xm with pn, which is the impulse train, like this. And what happens when you convolve with an impulse train? By a shifting theorem, you just take the signal and put it where the impulse is. So it's going to make now an infinite copies of xn. So if my xn is a signal like this and 0 everywhere else, I will convolve it with Pn, which is going to make one copy here, one copy there, one copy there, and so on, and is going to make a periodic version of the original signal. Okay, so this will take you guys a while to get. If you are still confused about this, I'm not going to repeat this because I've already done it several times. And as I've mentioned, you just have to read it a few times for this to make sense. But this is the proof. Okay, even in Oppenheim and Schaefer, this is how it is shown. At very so that's how we show that the xn here, the periodic version of this is just the original x convolved with a train of delta functions separated by n. So there's one delta function here, one separated by n. So every time I convolve the signal, I basically just put that signal there. This is the shifting theorem. Okay, and then it will just make infinite copies and be a periodic signal produced by taking xn and shifting it by n and concatenating them. Okay, so here's this is how we compute the DFS, DFT. Consider a finite length sequence of length n. Construct a periodic discrete signal which is given by this. It's xn between 0 and n, and then I shift it by n, so it's xn minus n. Then I shift it by 2n, it's xn minus 2n. So this is xn, let's say, between 0 and n, n minus 1. This is xn minus n, so it starts 2n minus 1. This is n, this is xn, this is xn minus n. This is xn minus 2n. So it will be a translated version there. And you sum all of them up, you get a periodic signal. Now, it doesn't matter whether you are working with this or that, because the two signals are the same between n0 and n minus 1. Xn is the same as x tilde n, and it's 0 otherwise. But the nice thing is this x tilde n can be represented by only n coefficients, because you can take its discrete Fourier series, and this is how it looks like. So I'm just multiplying it by e to the power minus j 2 pi by n kn. These are just nothing but the samples of the DTFT of xn. Okay. And essentially, now I have a Fourier representation of this signal, which has the same length as the signal itself, n. I take a signal of length n, I get its DFT, which is also a discrete signal of length n, given by this formula, and I'm done. I don't need to represent my aperiodic signal with an infinite number of frequencies, which was the case with DTFT. I can just look at the samples of the DTFT at n equispaced intervals, and I'm done. This is discrete Fourier transform. Okay. So here's a nice thing in Wikipedia that I found, which actually shows the different transforms very well. So this is on the left hand side, you have a continuous aperiodic signal, and this is its Fourier transform. Okay, so this is aperiodic, and this is its Fourier transform. Now, if I had a periodic continuous signal, I would take its Fourier series. The Fourier series is discrete, but you need an infinite number of terms there. Okay, this is this one. Here, this is the first thing that we did. This is the Fourier series, but you need an infinite number of terms. There are an infinite number of AKs, but they are discrete. That is what is shown here. Now, if I discretize the original signal, original aperiodic signal, I can take its DTFT, which will be a continuous function with a period of 2 pi. And if I now take the signal and make infinite copies of it, then I don't need all frequencies like in DTFT. I only need n frequencies that are samples of the original DTFT. And this is my discrete Fourier series, or equivalently here in this case, discrete Fourier transform. Okay, if you think of this as a periodic signal, you take its discrete Fourier series, or you can think of just an n samples here and directly use this formula. You get the discrete Fourier transform, and here you only need to worry about these many samples, n samples, which are samples of the DTFT, n samples of the continuous DTFT function. Okay, so now we will exclusively talk about DFT, because that's the only thing we can do. I give you some length 4096 samples. You always can only take the DFT of that, and it will give you n samples, and that's that. Okay, and you can always reconstruct the signal if you are given those n DFT coefficients using this synthesis equation. Okay. Okay, so I'm going to actually go back to the signal now and start showing and give you some little exercises also. There are two ways to understand Fourier analysis. One is through theory that we have done, but an equally powerful way is to just generate some signals in MATLAB and compute its Fourier transform and see what you get. And it's incredible how much you can understand just by doing this exercise. So while the math part settles in, which will require you guys to sit down and carefully read this over and over again, I will also show you how to do this in MATLAB, and it will actually be a nice complement to the theoretical work that you guys will be reading. Okay, so let's get back and actually see DFT in action. So here it is, DFT in action. I give you the LFP data. I have given you this, so you can, it's on the course page, so you can download it. And I'm looking at the first of the 76 trials. So Y is just a signal of length 4096. 4096. And if I plot Y, while mentioning what those 4096 samples correspond to in time, which is this time Wells function. This is also a function of length 4096. But it tells you that the first sample is minus 1 point whatever 1.1, the 600 sample is 0, and so on. So then this is what it looks like. And this is what you get when you plot the absolute value of the FFT. The first time you see this, it's always very scary. You'll say, hey, what the hell is this? This is the amplitude of the Fourier transform. How many samples does it have? 4096. Same number of samples as my original signal. So this is what you will end up getting. And notice that it's very hard to see what is going on, because at lower frequencies, the amplitude is very high and it quickly falls off. Also notice that it's symmetric about 4096, 2048. Okay, so whatever you get in the first, this part, it's the, it's the same in the other part. This is true for any real signal. Now I'm plotting the same function on a log scale. Now log, you can see very nicely that that power or the amplitude falls with frequency, like somewhat like. Okay, and we is clearer as we go. But this is the Fourier transform of the signal obtained simply by using this function FFT in MATLAB. Okay. So now you say, okay, this looks like a very tricky function here. What can I now get back to the question which I had asked with whether, my LFP has any oscillation? So first thing I need to do is find out what the frequency axis is. This axis is between 0 to 1 to 4096 samples, but each of them correspond to some frequency, right? So what do they correspond to? Can anyone tell me? What is the 4096th sample correspond to in the frequency domain? The DFT repeats after what frequency?
So we have, if we are taking K samples, so same number of samples we do take in DFT.
That's right. So here, so I'm looking at this little part here, right? I am asking what is this frequency? This is just the sampling rate, right? This is just omega s. So what we are seeing here, 4096 samples go from 0 to Fs sampling rate, which in this case is 2000 Hertz. Notice that I have to provide you this information. You can't get this information just from this because this is in samples. DFT is something just a number between 0 and n minus 1 or 1 to n. But what that n means in terms of actual frequency has to be provided to you. So here the sampling frequency is 2000 Hertz, which is something that I have to tell you. Otherwise, you can't find out. But once I give you this, I can actually create a frequency axis, which is nothing but 4096 samples spanning 0 to 2 Hertz. So 2 kilohertz. This is that function YS. I am dividing 0 to 1 in 4096 spaces. So it's 0, 1 by 4096, 2 by 4096, and the last one would be 1 minus 1 by 4096. So there are 4096 points between 0 and 1, and then I'm multiplying that by 2000. So I'm now getting 4096 points, which are equally sampling 0 to 2 kilohertz. That's this function. So now if I plot YS and abs FFTY, this one is just giving you the samples between 0 and, what each sample means in terms of frequency. I'm getting the values between 0 and 2 kilohertz. Okay, and now notice that after 500 hertz, there's a bit of a fall here. And this is the action of the filter that I had applied to the original LFP signal, original signal before I was sampling it. But notice that it's still quite crappy. So what do I do? Well, and remember now that I have got 76 such trials. So I can say, all right, let me look at all 76 such trials, and this is how they look like. This FFT function can work on arrays directly. So this is the command that tells you to apply the FFT on an array along the second dimension, which is at 4096. This is a 76 cross 4096 array, and I am telling it to apply the FFT on the second dimension. And this is what it gives me. Still looks very noisy, but when I look at the average, this is what I get. This is the log amplitude of the FFT. Mean log abs FFT. Okay, and now you can see some structure in the signal which looks slightly better than before. What's the structure here? The structure is that the signal has a lot of energy upfront here, and as frequency increases, the power falls, then it sort of settles down, and after 500 hertz there's a further fall, and this is the action of the Butterworth filter that I had applied. So there was a Butterworth filter that was applied. I will tell you again why we applied that, but you can see that in the signal if you look at the FFT this way. Now what is this thing here? Why do we have a spike there? Anyone? Where is this frequency approximately? What do you think is this
Noise.
This is line noise. Very good. So if I zoom in, oh, sorry, this is not 50 hertz. This is actually 100 hertz. This is the second harmonic of the line noise. Usually our signals are so well shielded and grounded that you often don't even see the line noise. Line noise would have been here, somewhere here. Often we do see that also, but here this is the second harmonic of this. But actually, in this case, this is not the noise because these recordings were actually done in the US. So there the line noise is at 60. It's a bit of a peak here at 120. But it's very good shielding, so that you don't see it. This 100 hertz is actually the monitor refresh rate. The monitor that the monkey is looking at is refreshing at 100 hertz, and that is what produces actually a signal. There are some cells that actually get locked to the refresh rate. So this is not just noise, this is also some biophysical signal here. Okay. So one more thing before we wrap up for today, and then we will carry on from here. Now, you guys really have to come to this stage for us to make progress further. Okay, so you have to really go back and read, otherwise things will just fall apart otherwise. Because we are going to talk about windowing, multi-taper, wavelets, Hilbert transform, a bunch of more advanced things, all of which rely on the Fourier, understanding of the Fourier analysis. So you'll have to think about, you'll have to understand the math well enough so that you can at least follow what is going on here. Okay, so one last thing before we wrap up. Can anyone think and tell me what's the frequency resolution of the signal? Which means that in the frequency axis, how far are the points? If I look at one point and another point, what's the distance in the frequency axis?
What? By distance, what do you mean? It's like
Well, so
now.
each point is some frequency, right? So here, well, okay, so this is this YS was clear, right? These are 4096 points, and I'm asking what's the distance between YS2 and YS1, let's say. What's the spacing in frequency between any two frequency values that are? See, the DFT is being computed at only a discrete number of points. It's not a continuous function. So this is the frequency axis, and you've got a bunch of points, but not an infinite number of points. So I want to know what's the distance between any 2 points. And actually the answer is right here. It's just Fs, which is the sampling frequency, divided by n. Now the question is, if you sample faster, suppose you sample, instead of 2000 hertz, I sample at 2 million hertz. The question is whether that's going to make my frequency resolution better, worse, or will it not change? Okay, so think about it. I won't give the answer straight away, but these are the sort of questions that will keep coming up as we try to represent the signal in the best possible way and look at its frequency components that are sitting there. Okay, and the answer that you may find to this question may be a little counterintuitive when you do this for the first time, but it will sort of make sense eventually as we dig deeper into this. This is very deep stuff actually. This Fourier analysis is not straightforward that way. So think about it, and we will look at the answer in the next class, and we'll go from here. Please do read what we have done so far. Otherwise, it will become very confusing.
Can you repeat the question once?
Well, the question is right here. What is the frequency resolution here? Which is, if I look at consecutive values, well, the first value is at 0, right? The first frequency FFT is at 0. The question is, what is the frequency of the next point? That is what I mean by frequency resolution. Okay, is the question clear? I am computing the Fourier transform at certain frequencies. The first frequency at which I've computed my FFT is 0. What's the next one? They are equally spaced. So the closer they are in frequency, the better is my understanding of the signal in the frequency domain. Here, for example, I can say that it's exactly at 100 hertz, but not 105 hertz, let's say. So the closer these points are going to be in frequency is better is my frequency resolution. So I'm asking, what's the frequency resolution? How do I improve the frequency resolution of the signal? Think about it and give me an answer in the next class. All right, folks. So from your, stop recording.